Thanks, Ian. So now we're going to jump into the project, and there is going to be some repetition from the Swan Lake project, but there's also lots of new information dealing with Rock Lake. It is a completely different system than Swan. Before we get into the project, like Cliff already said at the beginning, the funders, all of the funders, in the Tri-Lakes group that put money towards this project is essentially, making this project possible to move forward and basically get a better idea on how we could try to enhance these lakes from a fisheries perspective. And that is the goal, is how do we improve upon both of these systems to try to have sustainable fisheries. And last week, we discussed the options of building a dam and raising water levels on Swan Lake, and we'll get into the recommendations later on for Rock. A little bit of background. I'm not sure if everyone was on the call last time, but there's 3 lakes in the Tri-Lakes. Pelican Lake is pretty well at the headwaters. Then it goes through Rock Lake and Swan Lake. Pembina River, we're pretty well at the headwaters of the Pembina River here before it flows into the Rock, Swan, and then down, eventually getting into the Red River. So Rock Lake, Pelican, and Swan, they're all fairly similar. They all have lots of similar characteristics. Essentially, they're all shallow. They're all less than 6 meters. They all have soft bottom lakes. They're all eutrophic. And when I mean eutrophic, that means that they have lots of nutrients going into those systems. And therefore, that leads to, algal growth and challenges when you have lots of algal growth, right? Also, they're well mixed. So they're basically mixed from the top to the bottom, and they're susceptible to algal blooms. Rock Lake, different than Swan in the fact that Rock Lake is about 4.25 meters deep. So that's about double the depth of Swan Lake. So we're talking about a 13-meter depth overall, or 13 feet depth overall. Another thing that's unique about Rock Lake is there is a control structure on Rock Lake as we speak. So I can't, my mouse, your cameras are kind of over it, but down here, I don't know if you could see my mouse there moving around. Down here, 4.35 kilometers down from Rock Lake, there is a control structure there. And that control structure was built in 1941. And it was built basically to prevent this lake from drying up. It was built for a drought protection. And it was basically to regulate the lake at 405.1 meters. So 405.1, that is the number that people should remember moving forward, and I will bring it up, but that is basically the current level that the Rock Lake is supposed to be maintained at under low flow. So looking at that structure, this is basically the structure that is located downstream, about 5 kilometers down, and essentially it was built in 1941. It is degrading. So there, it's undercutting. It's not stable. It's something has to be done to fix up either this structure or decommission it completely and move to another structure to essentially prevent drought. So looking at the lake levels on Rock Lake. What you're looking here, hopefully you can see my mouse. This blue line here is essentially the minimum level that the lake will get to be 405.1 as a result of that control structure that was built in 1941. What this red line is, and we just picked a random year. You could go on Environment Canada and pick any year, but this basically just shows what the lake did in 2014. In 2018, it was a little bit lower. In other years, it was a little bit higher. The green bar that I'm showing you right here, this is the average. So this is the average lake levels within Rock Lake over time. And this just shows you January, February, March, April, May. So the different months are on the bottom of the scale. And then the heights, the water elevation is shown on the y-axis or the left axis here. What I would like to point out is these are the high values. That's this green line here. This shows you that the lake, Rock Lake, has actually got to 407.5. So that's 2.5 meters higher than what that dam was built in the first place at 405.1. So that just kind of gives you a background on where this lake is. So although that there is a dam regulated to hold water levels at this 401, you could see that the majority of the time the lake is actually higher than that level. It is only when you come down in the winter time that it actually gets back down to that level. So during this process, we had lots of meetings with landowners. We had meetings with the Tri-Lakes group. We met with the Pembina Valley Watershed District. And I guess the main point that people wanted to pursue with this study is recreational fishing opportunities. They wanted to improve the lakes from a fisheries perspective to try to draw more people, more tourism, build up the economy, have healthier water. Typically, if you have a better fishery, you typically have better water as well. Water quality was discussed. It's a big issue. And in the past, there's also been winter kills on Rock Lake, where essentially that there has been die-offs, essentially because of low oxygen level. And as I said earlier, Swan, Pelican, and Rock, they're all eutrophic lakes. And what that essentially means is that there's lots of nutrients within these systems. So the problem is once you put ice cover over top of it, what happens is microbial activity eats away at all of that nutrients, either SOD, sediment oxygen demand, or biological oxygen demand. So there's lots of organisms within the water eating away at that oxygen. And when you cover these lakes with ice, if there's not enough volume of oxygen within that system, as they degrade over time and over the winter, if it gets too low, you could have these fish kills. So that's one of the main causes of these fish kills. There's also aesthetic issues. When you have super high nutrients, you have these big algal blooms, and it essentially could turn your water, into a really bright green. And when we were out there in 2014, the water was greener than green. It was pretty amazing. So there is definitely issues in terms of how much nutrients is coming into these systems and degrading water quality. And I think that is the Pembina Valley Watershed District's prime concern, as to how do we prevent and how do we improve upon the water quality of these lakes. That's one of their main mandates moving forward. And talking about nutrients here, I'm going to turn this over to Ian for this slide. But essentially what it is this just shows that there's lots of phosphorus within these systems. This graph is actually showing of Swan. And Ian, I'll let you kind of cut in there and chat a little bit about this graph.
Well, these points here are showing measured phosphorus levels in the lake. And you can see that the levels are 0.2 milligrams per liter. Now, usually when you're talking about a lake, you want phosphorus levels to be down here, actually below this blue line at 0.02 milligrams per liter. In a river, we usually use 0.05, which is where this blue line is, to look at the level that you will start to encourage algae growth in the system. So if you don't want any algae growth, you must maintain your phosphorus levels down here. But up here, then you're going to get lots of algae growth. And what you can see here is up in here, we've got measurements that are at least 10 times higher, or 0.02, 0.05, 0.5. So you're looking at 10, 20 times higher up here than you would normally want in a lake to stop algae growth. So there's a lot of phosphorus, there's a lot of, shall we say, nutrient that's going to encourage algae growth in the lake. The other aspect of this that isn't shown here is total nitrogen levels. When I look at those total nitrogen levels, I find out that they're about 1.5, 1.6, 0.8, 0.9. But anyway, the point is there, I guess, is that when you're looking at a lake, you want to see the nitrogen to the phosphorus level at about 10 to 1 or 20 to 1 for a fairly healthy, shall we say, for a healthy algae growth, if you want to call it that. But if it gets below 10 to 1, the ratio, then you start to encourage blue-green algae. And what I've noticed with this lake is when I look at these concentrations, phosphorus concentrations versus the nitrogen concentrations, I look at those ratios and see that they're below 10:1. And that tells me that you're going to get a lot of blue-green algae in the lake, a lot more anyway than you would normally expect. And because the lake is becoming, as the algae grows, nitrogen limited. And those blue-green algae release toxins. And those toxins can kill fish, animals, and even humans. And they have also an effect on people swimming in the lake and that sort of thing. So when I look at the nutrients that are coming into this lake, I think, wow, we should be trying to do something to pull back those nutrients and to lower these nutrients, and also especially the phosphorus, because it's so out of line with the amount of nitrogens that are coming in. Anyway, I'll leave it there.
Thanks, Ian. Another thing that we looked at and assessed on this system is shoreline erosion, and now shoreline erosion on Rock Lake is a major problem. There have been many high water events on this lake that have caused erosion. As you can see, that there's a couple of images here where basically the shorelines are eroding, and they're going to continue to erode until that lake becomes at a 4:1 or a 3:1 ratio. So erosion is not going to stop on this lake. It's going to be a problem moving forward. And that's one thing that we did consider when we came up with our recommendations, which I'll discuss later on. So I guess the project objectives, one was to go in and get a better handle on the hydrology and get some water quality information. The other one was to conduct fish habitat suitability assessments to figure out, okay, what do we have to do to these systems to try to improve upon them, to encourage, healthy fish populations. And then obviously we wanted to, outline all of the enhancement strategies that we could come up with, include either damming or aeration or fisheries enhancement options to try to improve upon the current state of the fisheries within both and Swan. Assess cost benefit ratios to the project. And then finally, we're going to have this workshop that we're having now. And also we've provided the Pembina Valley Watershed District with a report of the findings, which I think Cliff is putting it online for people to download if they want to have a read. So getting into the fish and fish habitat. So we actually didn't go out and although that I'm a fisheries biologist and we do lots of fisheries assessments and we go out and do community composition, we could do population assessments, we could figure out how many carp are in a system or what type of fish are there. That wasn't part of this study. So what we did though is we went through the literature, we worked with the provincial government and just basically figured out what species have range distributions that could be in these water bodies. And we also talked to a number of locals. So there's about 6 or 7 common fish that you're going to find in these systems. You got white sucker, you got walleye. Everyone likes walleye or pickerel, pike, jackfish. There's lots of pike within the system. Yellow perch is the same thing. Also that these are very productive systems. So there are lots of minnows. There's probably stickleback mud minnows. There could be a whole whackload of fish. There's essentially 35 species that have range distributions that could be within this water body. And of those 35, we went through that list and we pretty well cut it down to about 25. Channel cats, you're not going to get there. Sturgeon, there's a number of other fish that just the habitat is not suitable. And those fish would have to come up from the Red River essentially to get within this waterway. So we are looking at a fairly, diverse fish community, and each one of these fish require different habitat types to, be healthy. The one thing is everyone wants walleye fisheries. They want walleye, they want walleye, fishing, great walleye. The thing is walleye feed on lots of the other fish. So you really need to have a good balance within your fish community to really support a healthy and a long-term fish community. So you need the macrophyte beds, for forage fish growth. You need those deeper areas for overwintering purposes. You need high oxygen for a different number of fish. So we're looking at those habitat characteristics. Swan or Rock Lake, 4.25 meters. The talk last week was all about Swan. Swan super shallow. We're talking 2 meters max depth. So this lake is already one up on Swan in the fact that there is depth, there is better habitat, and right off the pop, you could easily have a healthy fishery within this system. You're talking about 13 feet water depth. Looking at fish and fish requirements from the oxygen side, if you're going to get into trout lakes or have salmon, on the right it shows you what the fish are, and then it shows kind of what their oxygen requirements are. So when you're in BC or you're in a cold water system, those oxygen demands, typically you have really high oxygen. You have about 14 milligrams per liter within that water. And as you go down, you pretty well eliminate some of those top fish that really require cold water or they require lots of oxygen. Then you get down to salmon, you get into bluegill around the 10 mark, and these marks fluctuate, right? Every fish is a little bit different depending on temperature. And as you go down, you can see carp require about 8 milligrams. So carp actually require quite a bit of oxygen. So if you get into really, really low oxygen waters, carp will essentially die off. You go further down into walleye, now you're talking about 6 milligrams. Cliff has a question, or there's a question out there.
Yeah, well, while you're talking about fish, there's a comment that in 2018, there was a lot of big catfish in the lake.
Oh,
So
yeah.
do they come up in really big flood years, or can they sustain a population?
Well, there's no spawning, or I wouldn't think that there would be very good spawning habitat. That's really interesting. Like channel cats were in rock is what the comment was?
Yeah, 2018, 24 to 28 inch, which maybe isn't huge, but a number of them.
Well, that's very interesting. One thing about channel catch, which is also really cool, is they carry the glaucidiae, and that's kind of a weird word that you guys probably haven't heard before, but it's basically the babies of maple leaf mussel. And so maple leaf mussel isn't endangered, or it wasn't endangered. Now it's a special concern or a threatened species within the province. But essentially, for that maple leaf or that mussel to move, it needs to move on channel catfish gills. So it is host dependent. So wherever channel catfish go, it carries maple leaf mussel and drops out. So that would mean that you could potentially have a threatened species within these waters if the channel catfish got there. So yeah, that's very interesting. In terms of sustaining catfish growth, potentially, typically from spawning habitat, they like to spawn in, really faster waters in like Lockport area where you get lots of channel cats and things like that. But they do go into blood vein, and they're known on lots of river systems around Lake Winnipeg. So I don't know exactly if they'd be sustainable. I know in the Assiniboine River that they're very abundant and red. But yeah, I'm intrigued by that. I'm pretty interested by that. In terms of oxygen, getting back to the oxygen talk, walleye, we're looking at about 6 milligrams. 5 milligrams is basically what the literature says. Walleye, depending, some lakes you could find walleye where they actually don't die if you get a little bit lower, but 5 or 6 is what your target is for trying to sustain a really healthy fishery. And the thing is the little walleye might survive. The bigger walleye that might need more oxygen, those ones might kick the bucket once you really get lower. So it depends on the size of fish as well. Once you get down to about 3 milligrams, now you're killing your walleye off, and now you basically pike could withstand really low oxygen levels, and some forage fish like your fathead minnows and stickleback, so they will be able to sustain fairly low oxygen levels. But essentially you need adequate oxygen levels year in, year out, and essentially it's in the winter time that oxygen levels basically go down and they start approaching levels that become lethal to these fish. So it's really adequate in the winter time to prevent high oxygen. One thing I should also state is oxygen in warm water holds less oxygen. So the warmer the water is, the less oxygen it actually holds. So if you get these really high warm water lakes, you could actually have summer kill as well, depending on how warm temperatures get. So depth actually provides a cover for fish as well. The deeper you go, then the water won't get as warm, and it will be able to sustain a healthy fishery that way as well. So there are positives from both summer and winter to having more water. What we did in terms of suitability assessments, we went through and we looked at walleye. We looked at a whole bunch of things in terms of from the literature. There's basically these HSI models that you could look at, and it essentially evaluates each of the habitats in terms of water depth, in terms of dissolved oxygen, in terms of spawning habitat, and you could put a value on how healthy that lake is for that specific species. So we did that for both rock and swan, and in swan, it turned out that essentially pike were the only ones that were really suited for that lake because of the low oxygen levels and that there was lots of adequate spawning habitat. Where walleye, you need to have, you know, gravel, sand bar, or gravel and cobble bars for spawning. You need to have higher oxygen levels. So they were all ranked all the way through. Here we're just showing walleye and yellow perch. This one is northern pike and white sucker. And just to give you a visual on what those graphs actually mean, is essentially if you have a suitability index of 1, that essentially says that that habitat is really optimal conditions for walleye. So if they have lots of spawning habitat, then essentially depending on the substrate type, you will have, you know, healthy habitat. And we evaluated this for all those different characteristics. This one's looking at spawning index. This one's looking at littoral zone, because that's one of the parameters that will really determine whether yellow perch will be able to really sustain a healthy population, is how much littoral zone and how much weedy habitats they have for spawning and for cover and refuge and that sort of thing. So we evaluated that for each one of the species. Getting into the hydrology, a little bit of a background on the hydrology and water quality. I'm going to turn it over to Ian shortly, but I just wanted to talk a little bit about the field program that we undertook. Essentially, what we wanted to do is, because of oxygen is such an important factor in determining how healthy and sustainable you could have a fishery, we went out and we sampled right after ice off, and we sampled in January and then again in March. We were looking at how much phosphorus was in the water, so we did a full suite of analyses that was sent to ALS for analysis. We also were doing dissolved oxygen and figuring out how much oxygen is within these systems. We had a number of sampling sites on Rock Lake, and we also were able to piggyback off of some of the data that Cliff collected with the Pembina Valley, I guess, Conservation District at that time. Now it's the Watershed District. We were able to incorporate some of that information into our studies as well. I guess this is probably a good time to turn it over to you, Ian, just to talk about the flows, the lake levels, and you know what we were working with in 2019, 2020.
Okay, so this is what the hydrology of, shall we say, Rock Lake looks like. Here is what we were dealing with in 2019, and then what I did here is I added this curve around the corner here into 2020 coming through here. But basically, this is the water level that we were dealing with. Mark is showing, I'm moving my cursor, but I guess Mark, you're doing a pretty good job because you're following mine along, even though it's blind. But what you can see is the water level in 2019 here. And as you went into September, the water level was getting fairly low. And then all of a sudden we ended up with 2 storms. One was a rainstorm and another was a snowmelt event or a snowstorm. And you got this huge peak in the water level in 2019 in November. And this is the highest on record because you can see the maximum is in green. The maximum water levels recorded on those particular days is in green through here. And what you can see is in 2019, you had a huge, shall we say, fall event. The largest event in 30 years on record. And so what that gave us when we were looking at the water quality and how we were going to model it was we were really working with an anomaly with the highest year. I'd much prefer to be working with a model where we're dealing with, when we're working with it on that particular year, to be in sort of average conditions. But anyway, this presented a little bit of a, it gave us an idea, actually, in terms of how to approach a water quality model. We'll go to the next slide, Mark, here. Looking at the hydrology of the lake, one of the things I always like to do is like to look at the peak water levels that occurred in every year. And what you can see is this is the total record that we had. We had 1954 to 2018. And the reason we didn't have the 2019, 2000 and into 2020 well is because Water Survey of Canada takes about a year to 2 years to really vet those records and release them. So when you go on the site, you'll usually find that you're a couple of years behind the actual record or the date. Anyway, what we notice here is these are the peak levels, if Mark can point to them, as we move along through here. And in that gap that you're seeing Mark just jumped over, the record isn't complete. It isn't continuous through all of these years. In some cases, the gauge was down. In some cases, it froze up. Whatever the reason, there are missing years, and there are actually missing months within those years sometimes. But this is a good idea of the peak water levels that have occurred each year. Most of these peaks occur in the spring, also, although some of them are rainfall events. What we did is we ran a regression line through here to see what the trend was in peak water levels. And what you'll notice here is a slightly upward trend to your peak water levels, meaning that there's more water coming into the system in terms of peak floods. And it's a fairly low correlation coefficient, R squared of 0.25. But what it does tell me is that there is a gradual increase in the peaks. And you can see that that line, that or trend line, is upwardly moving. And from the 50s to now, over the 60 years of record or so, it has moved up probably about 0.9 of a meter in terms of your peak flow events. And if you look at this closely, you'll see that line at 408, and the level 408, Mark, if you point that out, there's one level above 408 back in the 70s, and then there's three very recent levels above 408 from the 2000s, 2008 on. So now this could be for two reasons. One is climate change, you would point out at a trend analysis, but the other could be drainage too, that drainage systems on the land are changing and that the water is getting into Rock Lake much faster too.
I just want to add on this slide here, and one thing that I think it is important to show is this 405. I want to come back to that number. 405.1 is where that control structure has been in place. So the control structure is actually down here at this 4051 right now. So I just wanted to point that out right now because it will become important in the discussions further on.
And there actually is one slide or 1 year back in the 50s, if you look at it, 1957, or is it 59, where the water level, the peak water level in the lake was lower than the minimum water level in the structure.
Probably due to evaporation, you're thinking?
Not quite sure why that is. It's probably the structure was failing, as I would guess, in holding the water level at that 405.1. So Mark contacted me to get involved in this project, and he said to me, Ian, hey, there's a DO problem with this lake. It looks like there's fish kills in it. It can't sustain oxygen over the winter. Would you come? Could you model it for us? And I said, yes, we can. That's what we do. And we looked at this and we put together for the lake a conceptual drawing of how we would see the lake work. And I wonder, Mark, if can you move your cursor around for me? Mm-hmm. So when I'm looking at this lake, let's have a conceptual look at it in terms of the summertime, the open water period. And in the open water period, when we look at a lake, what we say is, okay, where does the DO come from? Well, there's two sources of DO. The biggest source, perhaps, is aeration. And aeration, when we say aeration here, what we mean is recharge from the atmosphere. Air is going into the lake, it's mixing with the surface of the water through wind and waves, and it's mixing into the lake. And usually over the summer, depending on the temperature of the lake will be at maximum DO capability, which is usually around 14.6 milligrams per liter. And it will be, as we would call it, saturated with oxygen or saturated with air. The other source that we have for DO, or dissolved oxygen as we call it, is really air in the water, is the inflow. And depending on what that inflow is usually fairly rich because it's coming from a turbulent stream or some such, and therefore mix quite readily with the atmosphere, and is usually bringing in saturated waters, meaning that they are around 14.6 milligrams per liter coming into the lake. And then when we look at how does a lake lose oxygen? Well, it loses oxygen through two mechanisms. One is outflow, because the outflow is taking water out of the lake, which contains oxygen. And the other method that it is biological and sediment oxygen demand. Now, these demands are set up by the decay of organic material within the lake. The organic material is the algae and the plant matter that have died and gone to the bottom or are floating within the water column. And as these things die, when they do die, bacteria start to feast on them, shall we say, and break them down. And bacteria consume a lot of oxygen. And so that is what the BOD and the SOD is. The BOD is the floating organic matter that is creating a demand for oxygen for its decay. And the SOD is the stuff that is settled to the bottom. And it's creating a demand for oxygen too. Now, if we move from the open water system to a closed system in the winter where ice is formed, we now shut off the aeration to the lake, the largest probably source of oxygen to the water. And we've shut it off. And now the only source is the inflow. And we're robbing oxygen out of the lake with the outflow. And we're also taking oxygen out now with the SOD and BOD. So we looked at this question, and we do a lot of this. I've done a lot of it over my career, this type of modeling. And we decided that we would use a mass balance approach here, because we could, first of all, balance the water inflow, outflow, change in storage. And then within that, we could balance the amount of dissolved oxygen doing the same thing. How much is coming in, how much is going out, and what is in storage, and what is being used by the BOD and SOD. And we did this in light of the extraordinary year we were facing. Remember, I had said that the water level in the fall was at an all-time high, never seen before in the 50 or 60 years of record. And what that meant was that we had a chance here probably to figure out a worst case scenario, because what's going to happen is, because the lake was at an all-time high, as the winter progresses, we imagined that the lake levels would fall. And because the lake levels are falling, that means the outflow is greater than the inflow. And if the outflow is greater than the inflow, you're taking more oxygen out of the lake. So this became what I thought, marvelously, was a worst case scenario for the lake. It may not happen that often, maybe once every 50 or 60 years where you've got this, but the more normal situation would be where the outflow and the inflow balance each other. In other words, there's a net zero. And there, then what you're looking at is the volume of the lake and the amount of BOD, SOD that is being exerted throughout that volume. Now, the other major piece here in terms of our modeling is the assumption that we made that the lake was well mixed. And when that means, when you say it's well mixed, usually we would look at a lake that is about 20 feet, 30 feet, 10 meters deep, and we would start to see some, what we would call stratification in the lake. And therefore then what we would do is we would look at the lake in a much more complicated fashion as the SOD acts from the bottom and moves up through the water column, and the BOD is distributed throughout the water column. But we didn't need to do that here because it's a shallow lake, and we could make the assumption that a parcel of water moving through the lake will move up and down and throughout the water column as it makes its way from the inflow to the outflow. And therefore will be the BOD and the SOD exertion we could couple together. And so we came up with a model, and I think that's on the next slide. And this model actually shows the best case scenario, which is actually where the inflow and the outflow are about the same. There's a net zero. And the orange line shows the worst case scenario, which is the scenario, the actual scenario we faced in 2019. Now, these two lines, what we think is the lake in any normal winter will be somewhere in between these. The actual point that we're looking at will be somewhere in between. Now, if you look at the axes that we have, the y-axis on here, Mark, you could point to it, that's the dissolved oxygen level. And you can see in the fall, in the 1st of November in 2019, it was up at around 14.6 milligrams per liter. That's it fully saturated with oxygen, the water. And then as you trace down those lines, you'll see this exponential curve showing, if you go on the blue or the yellow one, these exponential curves that show the decrease in oxygen with time. And in our case, we're measuring it in days. So you can see the 50-day, 75, 100-day levels. I think this is a really, really neat way of looking at how oxygen is depleted through the lake. And when we look at the 100-day level, we're what, 3 months and 10 days usually into the lake. And in this case, that 100-day level is about the oxygen level that you would find in, well, November. If we take November 1st as ice up, when ice went on and the aeration was cut off, we would go to the end of November as 1 month, the end of December as 2, the end of January as 3. So we're talking about maybe February 10th, right about now, the 100-day mark. And what you can see there is you can see that now in Rock Lake, your oxygen levels in the best case scenario, well, are probably just above around 5. And in a worst case scenario, probably around 4 or a little less in terms of milligrams per liter. So that means if I go to the chart on the side, on the left side, we can see what fish are in danger of being killed in this thing or by these low oxygen levels. And you can see that carp are probably there, muskie, walleye, perch are all in danger. Now, these are levels, 5, 4, for example, pike at 2, walleye at, is it walleye at 5? I'm having a hard time seeing that number. Yep. What that means is the larger you are, the more susceptible you are to DO starvation. So if you're a mature fish, you're much more susceptible than you are if you're a juvenile or a small fish. And we had this problem up in the oil sands because we were designing, or at least I was designing, compensation lakes. Lakes that would offset the harm that the oil sands mine are doing to the terrain, because there we had to capture those streams and lakes so that it weren't flowing over the oil sands mine, the open pits. And we'd have to compensate for those ecosystems somewhere else. So what we would do is we would build lakes. And we had built lakes back in about 2000 well, one of the first ones was in the early 2000s. And I studied it because I wanted to know what was working and what wasn't. And what we noticed about this first lake that was constructed in the oil sands as a compensation was there were no adult fish in it. And what was happening is they had built the lake and with an inflow and an outflow, and they had modeled it very similar to this, but the oxygen levels were going down to about 3 and 4 milligrams per liter, and sometimes even 2, but not all the time, not every winter. In a lot of the winters, the oxygen levels were around, the minimum oxygen level would be 5 or 6. But when you got a long winter in the north around the oil sands up in northern Alberta, you would get the oxygen curve decreasing over time. And when you got a really long winter, severe winter, that's when the oxygen levels would run to about 3 to 4. And that's when you would get a killing of all the adult fish.
Yeah, so Ian, there's a lot of questions, not a lot of questions, a few questions about the connection between Pelican Lake and Rock Lake and kind of how they work together. So Pelican Lake will sometimes release water in the spring. It's got a control on it. And, you know, that might contribute to Rock Lake flooding. So there is a report from the province that studied that, and they have indicated, yeah, there is an impact. And I guess we'd like to give that to you for your comments on it, if you would review that study and see what you thought. But also in terms of oxygen, like what is the relation? Sure. When they release water from Pelican Lake, how does that affect Rock Lake's oxygen?
Well, it would depend on when they release it. Like you're saying in the spring, is Rock Lake still iced over, or is it starting to crack, and is the ice starting to go to candle? And I'm not sure. Oh, you're on mute, Cliff, and I can't hear your question there.
I guess it depends on the year, but I would think generally, if Pelican Lake is flooding, then they have to release. They're kind of in a situation where they don't have a lot of choice. They don't want to harm the neighbors, but you know, they're releasing, and Rock Lake is going up.
Okay, so I would suspect it's how that water moves, okay, that they are releasing from Pelican to rock. If it's flowing on top of the ice and it can get well aerated, and then it gets into Rock Lake, then it could be a source of oxygen to the lake and it could sustain it. The other hand, if it's flowing underneath the ice and it's coming out of Pelican and it's not well aerated, it's low in oxygen, then you're going to get low oxygen waters going in. So I'm not sure. You'd have to give me the report. I'll have a look at it. And then I would look at the time of year that it's, you know, what the ice conditions were like, or what the water conditions were like when it was released. So yes, I'd certainly look at the report and then give you my thoughts. So they do this in Alberta, and because Alberta is so much quicker in terms of its reaction because of the mountains, so they have very few days to prepare for a flood if there is a huge snow melt in the mountains or rainstorms that are happening in the spring on top of the snow. So they tend to move their lakes down in the fall because they don't want to be pushing water that is in a lake under ice cover that has become low in oxygen, and then push that water downstream. So they like to bring their lakes down in the fall before anticipation. And they're not that great forecasters either. This is just as a precaution against the snowmelt event. Anyway, I'd like to see the report, and I'll certainly give you my thoughts about it. So if we move to the next slide, is that okay? Mark?
Yep.
Don't fall asleep on me. So the best way to look at those exponential curves that we were just looking at in terms of oxygen depletion over the winter, once you've got an ice cover on Rock Lake, is, I think, here in the table. What it shows is the saturation level in the best case and worst case scenario. And Mark, if you could point to the 0 and 0, those are the days. Okay, so this is at the start of ice forming on the lake, 0 days. And then how many days under ice do you have? Number of days for DO level to fall, because there's an ice buildup on the lake through the winter. And you can see that if we look at the best case scenario, after 75 days, the lake has fallen to 6.5 milligrams per liter of oxygen, which is sustainable if we were to look back at that curve for probably pickerel at this stage. But after 90 days or 3 months, so if we have the ice cover going in at the beginning of November, we're talking beginning of December, beginning of January, beginning of February, Rock Lake is now looking at about 5.5 milligrams per liter according to the model. And then as we go another month to the beginning of March, we're looking at around 4. And if we get a really severe winter where the ice cover will remain into past March into April, then you can see how this will, the oxygen levels fall. And this is what we found was killing the adult fish. It wasn't that it was occurring every year up in the, well, even when we did it in the Northwest Territories too, but in Alberta, when we were building the compensation lakes, it's about, you would get these severe winters, 1 in 10, every 10 winters or every 12, 20 winters, and that would kill all the adult fish and in the lake. And what we were seeing was just juveniles in the lake. So something we've got to be careful about when we try to match these numbers against those sort of levels for fish kills that we were showing in that chart earlier. And here's the worst case scenario underneath that. And you can see that that exponential, although those two curves look quite close together, there is quite a difference in them. In terms of the worst case, if you have an outflow that is greater than the inflow, in other words, the ice is settling over the winter, what you can find is that within 3 months, you're down to 4 milligrams per liter underneath that ice cover. So this is an argument for aeration of that lake. If you want to sustain adult fish in that lake, you probably need, well, you need a source of aeration. And I've always thought that there are 2 sources of aeration you could do, and especially in these COVID times. One is to put in the aeration system, but the other is to take the snow off the ice. If you took the snow off the ice, drove around with a grader and I've forgotten the name of them. What do you call them? You put them on the ice rinks and the Zambonis. Drove around with a Zamboni. You'd have clear glass. And then what you would do is you would encourage all of that phytoplankton growth underneath. And the one thing that algae do is they give off oxygen in light. And they would replenish. And as a matter of fact, this has been noted in some of the Alberta rinks that they build on those ponds in downtown Calgary, is that those lakes seem to sustain fish. And why do they sustain fish? Well, they sustain fish because they clear off the ice or they clear off the snow. So it's another technique. And mind you, we're talking about a lot bigger lake here. Those are little ponds in Alberta, but it's just a neat little side. Anyway, moving on.